So, remember that at this point we've got the plum pudding / blueberry muffin model. We've got this big positive ball of stuff with these little negative charges scattered around in it. So about this time, Ernst Rutherford, who was basically a hick from New Zealand, he was a poor farm kid from New Zealand. He does, and his a quote that he repeated of his mother's was his mother said, "Ernst, we haven't the money, so you must be clever." Basically, you don't have means in this world, so you're going to have to be smart about how you do things. And he said later that sort of drove his resourcefulness in the lab. He was known as a very resourceful experimenter. So he comes up with this brilliant experiment. At this point, we think it's a blueberry muffin. We think it's the batter is all positive, and there are these little tiny lumps of negative in there. So he takes a piece of foil. You've all seen aluminum foil. It's thin, right? A piece of the thinnest aluminum foil you've ever seen is still multiple atoms thick. So he takes a gold foil that is so thin, it's really like about 1 atom thick. It's very, very thin foil. Takes that, lines it up, and then takes something it's an alpha particle emitter. So an alpha particle is positively charged, but it's basically a helium atom that's stripped of its electrons, except they didn't know that yet. Anyway, so you take these positively charged alpha particles, and he's firing them at gold foil. So this should be like taking a sheet of notebook paper and shooting it with a rifle. This stuff should go straight through. These particles you're firing are positive. As long as what we think is true, and the batter of the blueberry muffin is all positive, and there are just these little scattered bits of negative stuff, these positive bullets, as it were, these alpha particles, should pretty much go straight through. They might bend a little bit if they get close to one of these negative blueberries. They might wiggle over to be closer to the negative blueberry. But overall, this whole thing is positive. So while they're going to be repelled by the positive, there's enough negatives scattered throughout it. They should just go straight through. It'll be fine. They come right straight back at him. And Rutherford actually described this, and this is quoted in your textbook, as, imagine our surprise. It was as if we had fired an artillery shell at a piece of tissue paper and had it bounce back. Whoa! That wasn't supposed to happen. That's crazy. And some of these particles literally, did a 90-degree turn, 180, came right back at his face. And a lot of them just bent off at an angle. So clearly there's something else going on here. So he looks at this and says, you know what? I don't think all that batter is positive. I'm not sure there's batter at all. I think there's a little tiny lump of something positive right in the middle. And I think all this negative stuff is way out on the edges. I think these electrons are somewhere outside, and I think in the middle there's a little tiny positive lump. And when my alpha particles hit that positive lump, they come bouncing back. That's what I think. So this gives us Rutherford's model of the atom. And this is the one this is basically, with some modification, what you learned in junior high. It's what you learned in physical science. And we say that it's sometimes called the planetary model. It's like the Earth, the planet. The electrons are like a little moon orbiting around the Earth. Pretty much. Now, there's one little problem with this. Remember that science is tentative. Remember that it's the best we know right now. So Rutherford says, okay, I think I got it. Little positive planet in the middle. Little electrons orbiting like moons around it. And somebody says, so if the middle's positive and the electrons are negative, why don't they just get sucked into the face of the planet? Well, we don't really have a good answer for that. But we think we got it. They don't have a good answer for that. Why don't the electrons get sucked into the nucleus? They're opposite charges. What should happen? Why doesn't it happen? We don't know. We don't. Okay. So at this point, we've got Dalton's atomic theory, which we've kept most of. We've got some modifications to them. Some of those aren't even here yet. And at this point, so we're around 1911, 1915. This is just before World War I. Rutherford has proposed a pretty good model for the electron. We've got one minor problem, like why don't the electrons get sucked into the face of the planet? But other than that, it's a pretty darn good model. We know what electrons are. We know that they've got this charge. We're still not sure where all the mass is coming from, and we're still not sure what the positive bit that makes things electrically neutral is. So at this point, Rutherford has said the positive bit's in the middle, but he hasn't said what that is. He hasn't said what that middle part is. It's just a positive lump in the middle. Okay, we're getting closer. So this is interesting. This is about how important it is to understand what you're looking at, and about incorrect inference. So, have you all heard the name Curie before? Where? Ah, Madame Curie, Marie Curie. She was a Pole who married a Frenchman, adopted his last name. She became Madame Marie Curie. She worked with radium, she worked with radiation. She died of cancer as a result of her research, because they didn't understand the importance of protecting oneself from radiation in the lab. So she had huge lifetime exposures and died of cancer really young. She was brilliant. Her husband was brilliant. Family of brilliant physicists. Their daughter, Irene, was also pretty clever. And Irene Curie married Frédéric Joliot. Interestingly enough, this is in the 1920s. Her parents were concerned that he wasn't smart enough for her, that he was going to drag her down. Irene and Frederick adopted a single last name. They hyphenated their two names. She became known as Irene Joliot Curie. He became known as Frédéric Joliot Curie. They worked together professionally and published all their research under their joint last name. This was unheard of. Really, really cool. So they were a great team, except. So they're working on this whole problem of mass in the atom. And while they're working on this, they come up with an experiment. They're looking at what makes up the nucleus. They get results, which are good results, and they look at it, and they infer incorrectly. They make a series of incorrect assumptions about their own results. So, they're working, I think, in France at this point. Of course, science is international. In science, we communicate, we write in journals, we go to conferences, we talk about our results. They publish their results, stating what their inference about their results is. And James Chadwick in England, I think he was at Cambridge, reads their paper and chuckles quietly under his breath to himself. They're wrong. Chadwick knows they're wrong. Chadwick knows, without a doubt, they got the right result, but they didn't understand what they were looking at. So Chadwick replicates their experiment, gets the same result, and knows that he has just proved the existence of a massive neutral particle in the nucleus. That's the neutron. Chadwick wins the Nobel Prize for his work. I'm guessing that Frederick and Irene were not real happy about that. Yeah. Actually, Frederick and Irene missed out on 2 Nobel Prizes. There were 2 things that they did that other people got Nobel Prizes for, because either other people published first or Frederick and Irene misinterpreted their own results. Ouch. Okay, so this is good. We know there are electrons. We know there's a little dense nucleus. We know that, okay, neutrons are providing some of the mass. We still don't know why the electrons aren't getting sucked into the face of the planet. How are they hanging out in these orbits? So we're going to pause here for a moment.